So we have this kind of manifesto. So this is what we care about, and why we get out of bed in the morning is because we're working on trying to solve this MLOps Manifesto. And the manifesto is in the form of 4 tests. So you can kind of apply these tests to your own MLOps pipelines, and you can sort of form an opinion about how mature you are against the different requirements here. And so the first requirement is that your model training and deployment pipelines have to be reproducible. What that means, a good test for this is if I can come along 9 months later, if someone else can come along 9 months later and retrain a model that was trained by somebody else without even talking to them, with, let's say, an old version of TensorFlow on an old data set with on hardware that is sufficiently equivalent that they can retrain the model to within a few percentage points, then you've got a reproducible MLOps pipeline. And if 9 months later you can't because you upgraded the version of TensorFlow on your development machines and the data's gone somewhere and you don't know where the data's gone, the data's changed in your production database, then you've failed the reproducibility test. And if you fail the reproducibility test, then you're in trouble from a governance and compliance perspective in some industries. The second test is your MLOps pipeline accountable? And we talk about accountability from the same perspective that we hold humans accountable for their decision-making process. And one of the ways in which you do that is you say, on what basis did you make your decision? And the on what basis question with machine learning as a minimum requirement, not even going into the whole area of explainability, but as a minimum requirement, you have to be able to say what version of the data was the model trained on. And so you need to be able to track the model back to the provenance of where that model came from, what data it was trained on, by whom, and so on. The next point, and it's especially pertinent at the moment, is this collaboration requirement. So it has to be possible to do asynchronous collaboration. And this is something that software DevOps has got sorted, and MLOps doesn't yet, mostly. And this means that I need to be able to, for example, if my colleague Chris is working on a model, I need to be able to make a fork of that model, and I need to be able to make changes to it without treading on Chris's toes. So we both need to be able to collaborate asynchronously and get useful work done. Now, this has kind of influenced the design of what we're building to a large extent because we believe very much in the sort of GitHub pull request style of collaboration that the data scientists are familiar with. And there are some challenges in making that possible for ML. And then finally, the model development process has to be continuous. And so there are a couple of things that I mean by this. The first one is that the development process must be automatic. The deployment process, sorry, must be automatic. So it must be possible to automatically deploy a model into a staging environment or production environment without manually emailing Jupyter notebooks or TensorFlow files, sort of serialized TensorFlow models around, because as soon as you start doing things manually, then it introduces this possibility for human error. And the other piece is that you have to be able to statistically monitor your models. And this is interesting because monitoring models is quite different to monitoring regular software that you might deploy as microservices. And the reason for that is that when you monitor software, you can monitor things like latencies and error rates. But when you monitor when you monitor models, machine learning models, they can be giving you perfectly normal latencies and perfectly normal error rates. And the model can have gone completely haywire. And the reason for that is basically, if you already knew the right answer for what the model was predicting, then you wouldn't need the model. In other words, the production data is unlabeled. And so this means that it's challenging to understand the behavior of your model once it's running in production. So an example might be that I might have deployed a model for autonomous vehicles that classify road signs. And so you might have a bunch of cars driving around with models running on hardware in the cars and sensors, cameras basically, on the cars that are looking around for the road signs. And if you already knew what road sign the sensor was looking at, then you wouldn't need the model, right? But at the same time, it means that it's hard to understand the behavior of the model in production. And there are some solutions to this, including looking at the statistical distribution of the classifications the model is making, if it's a classifier. And then you can say, well, if the actual distribution of classifications drifts very significantly from my expected distribution, like the distribution that I used in training, in the training set, then maybe page a human, like fire an alert and get a human to look at what's going on, because either you deployed a bad model, in which case, well, you need to know about it so that you can roll back and so that you can figure out what went wrong with the new deployed model, or the world changed. And especially with things like computer vision, it's often surprising like how the models actually distinguish features in the data, and you can get stupid things like the computer vision model might never have classified any, or never be trained on any stop signs in the snow. And for some reason, it can't classify stop signs in the snow. So suddenly it snows over a large part of the country, and then your stop sign classifier stops working. And obviously you're in trouble, so you need to have that statistical monitoring. So those are the requirements, and so I'm going to talk about how we can try and address those requirements using MLOps tools.